Hi, it's Paul back again, this time with a script designed to illustrate convergence of sequences and series of points in Rn, vectors in Rn, and even matrices. I'm assuming that you ran the preceding script and installed the Matrices package. I still have to call the function library to make sure that I can draw circles, maximize the available real estate, set up an empty plot, and now let's look at a convergent sequence of points in R2. Remember, we generate infinite sequences by means of functions, so that in principle you could call the function for any integer n, and all I do is generate an x-coordinate, generate a y-coordinate, and concatenate them together. The last line of a function specifies what will be returned by the function. So when I call this function with argument n, I will get the nth term in the sequence. Now, to illustrate convergence, I'm going to set up not a target interval, but a target ball, and I'll call the radius of that ball, which in 2 dimensions is just a circle, epsilon. So there's the circle, and I want to see if the points of the sequence get inside and stay inside. So using a for loop, I will plot the first 10 points and write text under each plotted point to indicate which one it is. There you can see 1 through 10, and you see some of them get inside, some of them don't. 9 in particular was outside after 6 and 8 had been inside. Let's plot the next 10 points and see if we can figure out a plausible value for capital N. I see number 17 right on the left boundary, but it looks as though the subsequent ones are safely inside, so perhaps for all little n greater than 17 will be inside the ball. Let's redraw our target and plot points 18 through 40, and they do seem to be safely inside. Of course, being inside one of these balls doesn't prove convergence. I have to repeat it with arbitrarily small epsilons. I'll just do one more. There's a smaller target, and capital N of 44 look good to me because when I plot points 45 on in the sequence, they're all inside the ball. In order to prove convergence of this sequence, of course, I'd have to do this for any positive epsilon, and what I would conclude is that the sequence converges to the center of the balls, the center of the circles, the point x equals 2, y equals 1. Now let's look at a convergent infinite series, this time of vectors, because we can add vectors together and make infinite series. So don't worry about what this function does. You'll see clearly enough how x and y are being generated when I plot the first 4 of them. V of 1 gives me a vector of 1 unit to the right. V of 2 is half a unit pointing down. 3 is a third of a unit pointing left. 4 is a fourth of a unit pointing up. This sequence of vectors clearly converges to 0, but it can also be used to define a convergent series. Remember how we make sequences from series? We make the sequence of partial sums by adding together terms of the series. So I'll set up a variable to hold the x-coordinate and the y-coordinate of the sum, set up a nice empty plot, and for each value from 1 through 10, I will update the sum, draw arrows from the old sum to the new sum, and then store the new sum in sum x and sum y. And now you can see I've drawn both the arrows of the original series in red, and I've drawn in black, and I've drawn the sequence of partial sums in red. So the question is, what's the limit of the partial sums? And I just happen to know the answer. If I look at the x-coordinates, I get 1 minus a third plus a fifth, which sums to pi over 4. If I look at the y-coordinates, I get minus a half plus a fourth minus a sixth. You might recognize that as half the series that converges to the natural log of 2. And therefore, I expect that the limit is going to be a point whose x-coordinate is pi over 4 and whose y-coordinate is minus log 2 over 2. Or maybe I should have said the limit is a vector, since we're taking partial sums of vectors. So I'll set up a target ball centered on that putative limit and choose as the radius of that an epsilon of 0.1. Blank the plot, draw my target, and now I will draw the first 10 vectors. And a few of them miss substantially, but they appear to be zeroing in on the target. Let's see if n equals 10 is big enough. All I have to do is repeat that result, but this time I only draw the arrow if I is greater than capital N, and it looks as though they're all inside. So convergence is looking promising. I take an epsilon that's half as large. I choose a capital N that's twice as large. Repeat, but this time plot in blue, and it looks as though the blue arrowheads had made it into the second ball. And in principle, I could prove, I can't prove anything by just drawing diagrams, but I could prove by pencil and paper mathematics that no matter how small a circle I choose, eventually, if I go far enough along in the series, all the partial sums will get inside it. It's very easy to prove that if a series of vectors converges, so does the sequence of first components, the sequence of second components, and so on. It's slightly harder to prove if each sequence of components converges, the series of vectors converges. The first result, by the way, remains valid if you go to infinite dimensional vector spaces. The second one does not. For the final topic, let's look at a geometric series of matrices. One of the craziest ideas you've ever heard of, I imagine. Since geometric series converge only when the ratio is less than 1, we want something about a matrix to be less than 1, and what we're going to use is the length of the matrix. Treating the matrix as a vector, we calculate its length as the square root of the sum of the squares. Here is a matrix. The 4 entries are all less than 1. But the important thing is the square root of the sum of the squares is just barely less than 1. That guarantees convergence. So we're now going to sum the first 7 terms of this geometric series, the identity matrix plus a squared, and so on. And in order to do that, I need a variable to hold the sum of terms. I need a variable called power to hold the highest power that I've calculated. And then with each successive term, what I do is update the sum of the terms and multiply the power by a yet again to create the power of the matrix A that's 1 higher. And I'll print that out so that you can see what it looks like. And there are some of the matrices. And well, it may be converging, may not. We haven't calculated enough terms to be sure. Let's try with 50 and maybe we'll get a clearer idea. So I run the same thing, but only print the last couple. And now when you look at those, 2 successive partial sums are the same to 7 decimal places, so the series appears to have converged. What does it converge to? Well, everyone knows the formula for the sum of a geometric series. It's 1 over 1 minus the ratio. So let's take the identity matrix minus A, use the solve function to form its inverse, and what do you know? We get the same thing. So the formula for the sum of a geometric series works even for matrices. Now let's try exponentiating it. If you think about it, the formula for the exponential function, the Taylor series, is very similar to the formula for a geometric series. It's just that you've got an extra n factorial in the denominator. So that means I have to divide each power by n factorial. Since I'm a sloppy coder and often divide by n minus 1 factorial or n plus 1 factorial when I meant to divide by n factorial, I'm going to try a case where I know the answer, a diagonal matrix whose entries are 2 and 1. Write down almost the same code, except that you can see in the second line here, the one that's highlighted, when I multiply by the matrix B, I also divide by I plus 1. The cumulative effect of that is to give me an n factorial in the denominator. And when I print that out, I get something that looks as though it might be e squared in the upper left and e in the lower right. And sure enough, it is. So I've got it right, and now I'll try with the matrix A. Exactly the same code, exactly the same thing as summing a geometric series, except for putting that n factorial in the denominator. And now I have calculated the exponential of that matrix. So what, you say? Well, it turns out this is the secret of solving systems of linear differential equations, as you will see in the next script.